All right, hello again, and welcome to the San Diego Supercomputer Center's series of lightning talks on wildfire management and technology. My name again is John Porton. I'm the Senior Research Manager in the SciCore Division at SDSC, and I am privileged today to be joined by Scott Pokswinski. I even cleared the name with you, and then I still stumbled over it when I introduced you. Scott is the Director of Fire Science Applications at the New Mexico Consortium. That's a nonprofit research collaboration between universities in New Mexico, industry in New Mexico, and the Los Alamos National Laboratory. His recent work focuses on integrating remote sensing technologies with monitoring and modeling technologies to increase the quality and efficiency of data used by fire and land managers. He's going to join us today to talk about terrestrial LiDAR scanning, which is a really important data source for people who are interested in building high quality vegetation models that are used in tools like Burn Pro 3D. Welcome, Scott. Thank you for your time.
Yeah, absolutely, John. Don't sweat the name. My family's so far removed from Poland, I don't know how to pronounce it honestly.
Excellent. Well, I think that we probably want to start at the beginning because some of the people who are coming to this video are going to be relatively new to the idea of wildfire management and how we gather data about forestry and forest characteristics. So, what is terrestrial LiDAR? How do we use terrestrial LiDAR to measure things in forests?
Yeah, good question. So um, from its most basic level, terrestrial lidar is just a lidar data collection type technology that originates from a single point, right? And it's a ground based versus you've got airborne lidar, UAS lidar, mobile lidar is ground based, but also could be up in UAS. But terrestrial lidar itself is usually a terrestrial lidar unit and a tripod and a single point that is then scanned, and then you can get we've got for our monitoring programs we have these little nice simple ones that are you know little guys. You just push the button and it scans and it gets about 15 million points in about 3 minutes, or with our newer versions, something like 12 and a half million points in 45 seconds. So it's a really fast way of collecting structural data. Um, and with that, you get, locations in space where the light goes out, the laser goes out, it gets reflected back, and then based off of where the azimuth and the azimuth and the angle, it figures out where that reflection was, and then it applies usually a reflectance value, so like how strong it came back, and then in this case, in most cases, it'll have like an RGB value from the camera, so it'll try to line up an image that it takes with those points to color them. And they can, like this little guy has a range of about 50 to 60 meters, which is, perfect for sampling. But if you're doing something like a survey, then you need a big, $125,000, 50-pound machine. But so they range all over the place. But it's essentially, in its simplest form, terrestrial LiDAR is just a technology that scans from that single perspective and then only sees one thing, right? And so, we get at bigger areas by doing multiple scans and sort of sewing them together. We call that registration. So we register those scans together. So like if you think of like if the center point there is like the scan upside down, right? I then want to like bring in multiple scans if we're doing it that way. Or you can treat it like a sampling tool and just get the information that you get from that, and then you have sort of sampling effort and all of that kind of stuff. But it's just in its most basic form, it's a way of getting at structural data that we could never get at before. Just measuring where something is in space actually means something.
So, I mean, know that this is a layperson's way of being amazed, but there's like a single laser in that thing that's bouncing off of 12 and a half million points in 45 seconds and giving you color values, something about like it's all like location data and all of that in that amount of time.
Yeah, and it's about 45 seconds, because and it's taking pictures from the on the that unit. It's taking pictures at the same time, so it's doing 360 degrees, and so yeah, it's like it's just sending out pulses really fast and then receiving those pulses back and then dividing the speed of light difference by two and saying, okay, here's where the point was. So yeah, it's pretty impressive. There's some, on the higher end, you have to have the technical knowledge to understand because there's multiple times around things. And when you're having further distance points, there can be some confusion. But yeah, and with these types, which are called time of flight, the most basic, they're sending out multiple points, multiple pulses, and then those are getting measured. There's also sort of a full waveform version, or that's or a phase base that it's not sending out pulses, it's sending out waves, and it's lining up those sine waves and measuring the distance from them, and then saying, okay, that's the distance. And so
Wild.
it's yeah, there's a bunch of different ways of getting at it, but that's at its most basic. It's just sending out pulses, having it reflect back, and measuring the time difference.
I could probably learn about this all day. So when we're taking TLS in forests, just in a lay 30,000 foot perspective, what sort of data are you capable of collecting from a TLS scan from a single spot in the forest?
Yeah, so that's a great question. We're constantly surprised by what we're able to get out of it. From it's a very visual medium. Obviously, the folks that we work with at UCSD are doing an amazing job of projecting this data in a way that's qualitatively impressive. The first time I stood in the center of one of my plots. And I, with the VR glasses, and I'm jumping up and looking over shrubs and all of that kind of stuff. A little tear, no, but it was really cool. It's really impressive. I've got here an example of a point cloud, and you can kind of see, the detail. And this is Colorado's Front Range, one single scan here. Um, you can
Wow.
kind of see like, and essentially what you've got here, that the trees, it's on a hillside. But the other thing that we have is that you'll notice that there's that perspective costs something, right? So that single
Oh,
perspective, you can see this missing data there. Well, this was a pile and burn treatment. So they harvested and piled it all up, and so you get occlusion. So unlike other, top-down aerial LiDAR methods or some other imagery, you see missing pieces of the pie. And so, I mentioned registration before, and you can get around things that way, but you can also just sort of take a look at this data as sort of a sampling tool. So the crazy thing is back, in the 40s, and even before that a little bit, early foresters figured out something. You can Google bitterlich rod, and you can see, you can think of using some very similar point analyses to kind of get at how we would estimate basal area, or which is, for those, it's essentially an estimation of how much area, if you were to cut every tree at 1.3 meters, and then like how much area that is over an acre, right? So they can estimate pine dens or stand tree densities. You can use methods like that, or use a prism method, which I've got a prism right here, to sort of use these tools to estimate those kind of things, and from a single point. And that's kind of the same thing, but it's on steroids. So instead of just a few points of interest that you're collecting, this is like 14 million, right? So yeah, there's some disadvantages, but then we can also use it like a sampling tool. And with the terrestrial lidar, we do that, especially with these single pulse units. We can get full accountability of what every point that goes out from it. So here's all the points that return, but there's also points that are missing, right? So there's some that came right towards us, shot up into space. So if I know those proportions of, I can look at how open canopies are, right? And so there's a bunch of ways we can do that. And so I've got a slide here, I think. Besides this sort of really cool qualitative, I can see, and if you put yourself right in the center of where the scan was, like they do, like the folks at UCSD do, like you guys do, you don't see this missing data because you're seeing the
right.
same perspective that the LiDAR does, and you can look around, and there aren't these missing pieces of chunks of data, which is really cool for you to kind of say, like, okay, does the data that I'm getting from the unit match up with what I feel like it would be if you're a manager, right? So I can predict all sorts of fuel measures, but they could be like stats, right? But they can go to points to pano, or go put on the goggles and say, oh yeah, no, that looks right. Because so the qualitative part is important. It's something that I fought with forever as a as a researcher. I'm about the numbers, but in the end, like that's a useful tool. And so, real quick, I've got a slide here that kind of gives you an idea. So one of the outputs we have all these outputs that we can get to be able to get at other things. So fuel loading, for instance, it's a qualitative thing that we can get from imagery, but it's also something that we can get really fine scale predictions of. So these numbers you have are just a sampling. So each GAPDR right there is a that's all. Those are all plots. Those are all scans. But each of those numbers, you can imagine there's 250 metrics that we generate from a single scan. So out of those 14 million points, it's like, where are the points falling out of the point cloud? And those can help us to make predictions about where things are at. So we can also do some semantic stuff, right? So we can label every point as a tree, get its DBH and all of that if we can see it, if there's not any occlusion. But then we can also do things like this is some work we did with Louise Loudermilk where we're predicting fuel loading, right? So at the 0 to 30 centimeters, that's your surface fuels. How good are we with those metrics, building models to predict the fuel loading? So the first one up in the upper left, that's, for instance, that's the total, or that's the total, that's all of the data. No, I'm sorry, that's the pre-burn data. The one next to it with 0.67, that's post-burn. So we did this pre-burn and post-burn. And then you can also just like look at the difference in the consumption, and those line up really nicely. So these are just a couple of ways that we can get at, or things that we can get from this terrestrial LiDAR data that are unique. And so first place I always go when I build a model, we can get all this stuff directly downloaded from Intellimon, which is our interagency ecological LiDAR monitoring program where data can be accessed. I go here first and I start doing some modeling, and I just start to do some variable selection. And that has been, we're blown away, but we're constantly able to predict, soil nutrients, and you're not measuring the soil, right? You're measuring the structure that may inform the nutrient cycling, right?
There's a
So
correlation
there's a
between the
correlation,
soil structure and the structure of the stuff that comes up out of it, I
and
suppose.
you get really ridiculous, like 0.6 to 0.9 level from just a couple of variables. It's really impressive. We've got some habitat stuff with some sandhill cranes and some other things. It's just a wealth of unexplored data right here. And so getting at the tree stuff, yes, this does do some of that. As I mentioned, that stem segmentation, we can do some, but it's not perfect because there's occlusion. But we can also model towards those numbers, right? So
Yeah.
there's a couple of ways that we can get at it.
So yeah, that's extremely fascinating. So thinking, I mean, that's not a CSV with 14 million rows, though, is it? The thing that you just showed me?
It's a CSV of 200, so it's not the points themselves, right?
Oh, it's not the points themselves. Okay.
No, so when you upload your data to Intellimon, we have a process that we go through, a workflow that has all of these analyses that we run. And so it's things like what you're seeing there are things like the kurtosis of the histogram of points at height in between 0 and 1 meter, right? So or the number of shrubs that we find. So there's a bunch of things that we do. Like we do go in and we classify stems that we can find, and we remove the stems and we crop everything at 3 meters. And we do some airborne LiDAR based analyses and say, okay, this is a shrub, this is a shrub. And we do convex hulls, and we do things like some nearest neighbor analyses, and we break up the point cloud in like I said, 20 to 30 different ways to come up with these 250 metrics. And they're just they're useless on their own, but they make good model variables.
Interesting. So when you're using those data to build models, where do you start? What are the analysis tools that you use?
I work in IntelliMon itself is all in R. I work in R. I do some variable selection methods like leaps and bounds is a popular one. There's a bunch of variable selection tools packages that R uses, and so once you get the training data, so you get obviously the actual measurements of the things you're trying to model to, you then can build set aside a testing set, and then you just model towards them. You do some variable selection, analyses. Like I said, leaps and bounds is a great method to just starting out. You can do all sorts of different ways of predicting, but they're usually linear models. But then you can use general additive models, gradient boosting machines, random forest, all sorts of ways. And then Telemon, then if once we build those models, we can then append them on to the end of those 250, so that every time something's run or added, if you've got a model, it'll add onto it. But then we also, because of that, do kind of stick to more basic machine learning and not get in too much into the deep learning, just because when someone uploads 50 scans, we want them all to be done in 5 minutes or less each, right? So you
Mm.
don't want a whole lot of we'll get there, with as we start getting more and more computational resources, but we want it to be fast and quick and easy, and just a pretty decent model, right? So
Yeah. So when you're thinking about attempting to create a vegetation model from this data, what is the relative role of the point cloud versus the characteristics that you just showed me?
yeah, so the point cloud itself, you know well, there's a couple. So one of the paths that I think we'll end up going down that is more on the deep learning side is to utilize something that the tool that has been developed, that the points to pano tool that's been developed at UCSD, where we take that point cloud and we just sort of rasterize it into a spherical raster, so that you can, and that's up on on the web too, so that you can go visit every plot that we have up on IntelliMine. You can look around and all that. But if you can then take that and use that raster to then say predict a vegetation type, that's some deep learning stuff, and we can do that. There's also some work that we're doing with something that was really developed for sort of the neurosciences. It's called topological analyses, which is essentially looking at point relationships to each other, and we find that we're able to separate different vegetation types out by how those points are related to each other, using something called Betty numbers. And I'm not going to get too deep into it, but essentially it's like how close those points are to each other, and like they all make connections as you increase a radius, and when do those points die and when do those points are they born, and they come up with these numbers that then just say, okay, there's a correlation to this habitat type versus this one, and how those sort of structures build. They use them. They originally developed them for like mapping neurons in your brain, but they work really well with point clouds. So yeah, so there's the raw point cloud we can use, or we're starting to get to use, and then there's also these raster products that we can then use deep learning for.
So, I mean, there's sort of a question that arises from this, which is if you want a really great vegetation model, why don't we just terrestrial LiDAR all the forests in California?
So that's a great question. It's tricky, right? So, oh well. So first of all, there's a lot of work that goes into that. So, I talked about, getting first of all, needing a big enough sample size. But the other part is, the limitations of terrestrial LiDAR. All of these tools have limitations. Airborne LiDAR, like terrestrial LiDAR, is great for seeing vertical points that you can't see.
From
That
the
you can't see
top. Yeah.
otherwise. Yeah, it's all, yeah. There's missing data, and the same with imagery and all of that. But the problem, I mean, it's synoptic, right? So you get this big total overview of the forest. You can do some of that with terrestrial LiDAR, but the amount of work that goes into it. So for instance, here, let me share my screen again. I've got an example where someone did ask me to do about a couple acre or a hectare area. So this is about 70 scans. And you can see like this is just a little small patch of land, right? And these are all individual trees in a plantation. So first of all, this is a ton of points. This is like 188 million points, and that's after I've done a lot of cleaning and removing of points. But I also have to match up every one of those 77 scans perfectly. So while this took me about a day to do walking through the woods to capture all of that data, it was probably a week and a half of manually lining up all 77 of those point clouds to get at this really fine scale structural model. And then the other part of it is now it's just this huge monster of a data set. You can tile it out,
Yeah.
but just like airborne LiDAR, but it's got all of the level that you would expect from maybe a really small airborne LiDAR flight. Well, not, I mean, like extremely small, but it's got the vertical detail. But the problem there is like the amount of work that would go into doing that. And if you're talking about, you know, if your question is, if we're doing it from single scans, what, would that be? We're working on that. Like we absolutely need to get more people out there with lasers, and we need to start going in that direction.
Yeah, it sounds like there are resource constraints. And then also talking about occlusion, sorry,
Yep.
got something caught in my throat.
All right.
Talking about occlusion and some other issues like building these cross-registered images takes a lot of time and a lot of resource. All right. If you were to give advice to someone who was looking at a terrestrial LiDAR data set who was thinking about building a vegetation model from first principles, what would you say?
Yeah, I mean, I always go back to the metrics file. So Intellimon has some outputs. Besides the metrics file, it's got, if you take the full output from the scan, you'll get a little really fine scale DEM. You'll get a canopy height model. And those are great. Those are great raster products. And especially if you're trying to match those up with airborne LiDAR, those might be a
Oh,
clue. And honestly, that would be a path. There is a little bit of some integration pieces, but and there's also sort of this sort of shrub model that we call fuels, which are shrub fuels, which is also a raster product that I kind of alluded to. But I go to the metrics every time because those have been consistently good, and yeah, I mean, and so honestly, I try to throw I try to like throw the whole toolbox out and see what sticks, or throw it all up on the wall and see what sticks. And the metrics typically do, but some of these raster based products, whether it's the rasters that come directly out of the point cloud, or whether it's the points to pano and some deep learning stuff, whatever your particular method is, we probably have about 7 or 8 analysts that build these models that are from different research groups, and we all have our own methods. I've got a buddy who was at Yosemite who just went to Redwoods, was the ecologist there, and he likes GAMs. I've got a modeler who works for me that really likes gradient boosting machines. I like leaps and bounds and just basic linear models because they get you there quick, and they rarely are beaten. But just making sure that you're doing things like, and this is key, making sure that you're looking at the assumptions of those models, not overfitting, limiting your variable selection to something that's reasonable, because overfit is an issue. Because you have 250 metrics, that can also be there can be a lot of there can be a lot of overlap and correlation between those variables. So you want to make sure that I use a package in R called performance to test my models, and look at where there might be some flaws. But there's a lot of ways. But just making sure that you have rock solid models, and the metrics is really the best way to get at it.
awesome. Well, I think that I probably speak for a lot of viewers when I say that if you ever are hiring for the job of going out into the forest and taking pictures, please keep me in mind. Scott, thank you so much for joining us. This has been extremely useful and interesting. And for the rest of you watching, of course, join us for the rest of our series of lightning talks. We'll see you there. Thanks a bunch, Scott.
Yeah.